Thank you for inviting me to speak in this session. It's been extremely interesting. This work that I will talk about today is a collaboration between myself and my student Simon Locke and Sujoy Mukhopadhyay. I'm looking at the evolution of volatiles as the planet is growing. And our focus for this talk will be on what happens during giant impacts, but I put up this image to remind you that the smaller bodies also play a role, but as Eric Asfog says, the unresolved debris in planet formation is much harder for us to quantify at this time. So I'll start with conclusions because we're rather late in the week. And the two things that I want you to remember from this talk are that giant impacts may remove substantial portions of the atmosphere on a planet, but it requires rather high impact energy and the presence of an ocean before the impact. And because of the ability to remove part of the atmosphere, there is the potential for elemental fractionation between volatiles. And I will describe that in more detail, but I want to caution you there's not isotopic fractionation as a result. And second, full mantle melting is quite difficult on larger protoplanets, and I will go through the details of that. And this is the mechanism that we proposed in order to be able to preserve primordial noble gases in a portion of the lower mantle. And so I'm emphasizing that it is quite difficult to make a full mantle magma ocean during a giant impact. So this talk is based on impact modeling results, and just to introduce you to the concept of how atmospheres are lost during giant impacts. These are cutaways through the equator with a density contour showing the cores and mantles. And this front is the shock wave that propagates through the body, here now on the other side of the core. And when that shock wave breaks out at the free surface, it causes surface motion that kicks the atmosphere. And if it kicks the bottom of the atmosphere fast enough, it can propagate a shock wave up through the atmosphere that can reach escape velocity. And so the pressure field, as you can see, is heterogeneous, and the shock decays as it propagates through the planet. The contours of shock pressure that I show down here are plotted in their original locations, but as you can see up here, the planet will move and readjust after the impact. And the shock pressures we're talking about are considerable, hundreds of gigapascals to 1,000 gigapascals for the highest energy impact events we expect during planet formation. And at these high shock pressures, one can begin to vaporize portions of the mantle. And the magnitude of atmospheric loss is related to this pressure field because surface motions are faster if there's a larger shock pressure gradient and slower if there's a more shallow pressure gradient. Also, there's more melting when you have higher pressures, so they are correlated. I'm using the hydrocode CTH. We're considering basically the whole range of terrestrial planet formation giant impact space, so many mass ratios of projectiles over the range of growing terrestrial planets at different impact velocities and different impact angles. The impact angle and velocity dependence is extremely important in the outcome of giant impacts, as you saw in some of Eric Asfog's movies. Here is an example of a 45-degree impact onto a half an Earth mass body, showing just a color scheme of the surface velocities on the planet induced by this event. And here's a histogram of the surface velocities as in kilometers per second, and this bin is everything greater than escape velocity, which is this red zone. And so there's a distribution of surface velocities, and for each surface velocity of the ground, we use a one-dimensional calculation of the gas loss above that parcel to calculate total atmospheric loss. So it's a combination of 3D hydrocode impacts to derive the field on the surface of the planet, coupled with a one-dimensional loss calculation to determine total atmospheric loss. And this is what it looks like. Total atmospheric loss as a fraction of the pre-existing atmosphere versus specific impact energy. So this is a measure of the kinetic energy of the impact over the total mass of the bodies, and it's adjusted by a factor that normalizes for the specific geometry, the mass ratio and the impact angle, and also makes this variable applicable to both the larger body and the smaller body involved in the impact event. The crazy mess of Symbols is just the parameter space that we explored, and these energies will be put in context in the middle, but at low impact energies, very little atmosphere is lost. Negligible is ejection near the impact point. And then there's about a decade where there's a log linear regime reaching near total atmospheric loss. This particular data are for bodies, are calculations of total loss without an ocean. When an ocean is added, there is more loss because the shock wave that propagates from the solid Earth into the more compressible ocean leads to decompression of that ocean to much higher velocities compared to the solid planet. So the liquid water, as it's shocked and decompresses, can kick the atmosphere at a higher velocity than the solid Earth, and that leads to an increase in the loss for the same specific energy of the impact. And it is quite difficult to blow off the ocean itself, and ocean loss criteria is basically the same as trying to blow off the crust of the planet. The surface needs to reach near escape velocity. Now, to put all of this, so what we have developed, and there's a paper in prep by Simon Locke and colleagues, where what we have is a function for any impact scenario, any pre-existing atmosphere and ocean mass and composition, we can give you a number for how much of the total atmosphere is ejected by this mechanism. Here is a histogram of the specific impact energy distribution in the giant impact stage of terrestrial planet formation, and this is taken from a suite of simulations by Sean Raymond. Other simulations of the same regime have similar histograms and specific energy, and this decade of 10 to the 6 to 10 to the 7 is the regime where there is significant atmospheric loss with an ocean from little loss to total loss, and it is the mode of giant impact events, and there are some events that have very little loss, and most of the smaller guy, the projectile and the impacts, experience substantial atmospheric loss just from that initial shock wave that occurs during the first hour of the contact between the two bodies. And so what we have are a range of outcomes that can occur in terms of atmospheric blow-off during the giant impact events that can lead to heterogeneities between the terrestrial planets. And I've noted here the impact energy range for the moon-forming giant impacts. It's quite hard to lose any atmosphere when there is no ocean present, although they are expected near the end stages of terrestrial planet formation. And so if one can blow off most of the gas, the atmophile materials, but retain most of the water in these energetic events in this mode of terrestrial planet formation, then that can lead to fractionation in volatiles by preferentially removing atmophiles and keeping water and volatiles that are soluble in water or the solid planet. And so this can lead to bulk fractionation between major elements such as hydrogen and nitrogen, which are observed in the Earth compared to chondrites, but it is not a one-to-one correlation, and so because it is not considering the budget of volatiles in the solid Earth. Okay, so the second part of the story is how much melts, because we'd like to know the depth of the magma ocean for reequilibration with the atmosphere as part of the story of volatile transport during growing the planet. Here are the histograms of shock pressures that you've already seen before. These specific examples are from potential moon-forming impacts, but what I want you to note is that the pressure field is significantly less in the antipode hemisphere compared to the impacted hemisphere. And this is because the wave decays as it travels through the planet, and it reflects at the core mantle boundary at the antipode of the planet. And so there's always a big drop in shock pressure from the core into the mantle on the antipode. These again are equatorial slices showing the jump in shock pressure spatially. And so the antipode experiences much less shock heating, and that material therefore is less heated and less buoyant as the planet reequilibrates back to a sphere during the giant impact event. And so here's a color code of a giant impact simulation where the colors just represent where the material ends up. Again, equatorial slices in time snapshots. So here at the end, the purple just denotes lower mantle material, and it originates from the antipode of the impact event where the material was least heated, and during gravitational readjustment ends up as the least buoyant and forms the new lower mantle. Now, the pressures involved in the antipodes of these very high energy impacts are jumps in shock pressure up to about 200 gigapascals. How much heating occurs during that? So I'm going to show you a phase diagram for the enstatite system. Here's the melting curve and enstatite, bridgmanite now, and the post-perovskite phase. And these are shock temperature measurements starting under room conditions. And we can calculate with model hugonios the temperature in the shock and the entropy increase from the shock event, which is quite considerable when one begins at the surface of the Earth. But if instead, here are model solidus and liquidus for the mantle, if we start in the mid-mantle at 50 gigapascals and near the solidus and shock from that initial state, bridgmanite is so much less compressible than lower pressure phases that there's very little shock heating and very little gain in entropy. So one can compare the increase in temperature along the hugonio beginning in bridgmanite compared to an isentrope starting at the same location, and for a jump in pressure of up to 200 GPa, there's negligible heating. And so if that parcel of material returns to the lower mantle by readjusting and staying in the lower mantle, it would not melt. Okay, and so the antipodes do not melt from this initial shock wave, and to caution you, half-space melting laws do not apply because of the geometry of these impacts and the sensitivity to the impact angle, and can be off by 2 orders of magnitude. So I caution the world not to use half-space calculations in their estimates of melting. So what I've calculated is the volume of the planet that would melt just from this initial shock wave, and not from later deposition of energy. So this is the volume of the mantle that will melt just from the initial shock, which is a portion of the total energy budget, versus the same specific impact energy, and this is the regime for atmospheric loss. And one can see that in these very low impact cases, the actual impact event is a hit and run, like Eric showed in his movies, and they negligibly melt the planet. And then once one approaches more head-on collisions, one can melt significant amounts of the mantle. But these events are quite rare and are more applicable to the smaller body in the impact event compared to the larger body. And so the initial deposition of energy by the contact and the shock actually melts very little of the planet, but everyone has heard that the kinetic energy of an impact event is sufficient to melt the whole planet completely. And the problem with that interpretation is that the energy of the impact is deposited extremely heterogeneously, and instead of melting the whole planet, we vaporize the impact hemisphere of the planet. But that's not our total energy budget. For head-on collisions, it's nearly the total energy budget, but in a grazing collision, the hit and run continues on, and the body's kinetic energy is not fully deposited as heat. There could be secondary impacts from debris, but those are mostly deposited on the surface of the planet that you've already melted. So you end up superheating above the liquidus, the melted portion of the planet, and preserving a portion of the planet in partially molten or not molten state. And so the two questions that I sought to address today are, do giant impacts melt most of the mantle? And the answer is usually not. It takes a very high energy collision in the context of terrestrial planet to melt the whole mantle, which is good if we want to preserve noble gases in the base of the mantle. And giant impacts do stochastically remove a portion of the atmosphere. They do contribute to the story of comparing Earth's volatile composition to the primitive materials that we are built from. The post-impact mantle is hot at the top and cold at the bottom. The lower mantle could survive for any of the suggested moon-forming impacts, and the cumulative effect of small and large impacts are likely one of the key factors in explaining the differences that we see in the volatile budgets between the terrestrial planets. Thank you.
Thank you very much. We have time for one quick question.
Hi, Sarah. I'm not really sure this is a question, but I do believe that the mantle would, in fact, melt completely. And I believe it is so because the antipodal hemisphere will collapse under its own weight, and the energy released by collapsing is sufficient to melt it, as Tonks and Malash pointed out. There's no place for the energy to go, so it's going to have to melt it.
So it doesn't collapse. I mean, it flows in the readjustment for the whole planet, but that deposition of energy comes from what in your mind?
It's just gravitation. The antipodal hemisphere will collapse under its own weight because it doesn't have the viscosity to stand up to.
It is not.
It just can't sit there as half a world solid.
So the gravitational readjustment is not from a static hemisphere readjusting to the lower mantle. The dynamic motion of the impact event is allowing it to flow around into the post-impact structure. And so numerical simulations that are run completely to the end do not heat the lower mantle.
And the second
completely.
reason it melts is because the top of the core is superheated by hot iron that came in from the impactor.
Only if the heat.
That's my opinion.
Only if the heat doesn't go down into the core. And so if the heat is distributed through the core, then you could prevent melting of the lower mantle. But if the heat is distributed into the mantle instead, but the core is more conductive, so in my mind, the heat goes down instead of up.